Okay, so first things first is talking about how it is that we draw angles in the Cartesian plane. So we call this standard position. An angle is in standard position when it's centered at the origin. So that means that the angle part is here. So this is where the corner of our angle will be, and we'll kind of build off of that. So always in here. So sometimes we draw triangles when we're in the Cartesian plane, and this angle that's in the other top corner, this is never the angle that we're talking about when we're in the Cartesian plane, okay? It's always, always, always a focus around the origin. So the terminal arm and the initial arm are the two lines that make up your angle together. So the initial arm is on the positive x-axis, so it's here. Okay, so this is the initial arm. And the terminal arm is wherever the angle ends, okay? And I always remember that it's called the terminal arm because if you think of, well, there's two ways to do it. So if you go to a terminal in real life, that's probably an airport or a bus terminal, the idea is you're going somewhere. So the terminal arm is the arm that can move around the circle. So it could be here, 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 here. It could be anywhere around the circle, whereas the initial arm is fixed. Okay, this is always the place where we start, and the terminal arm is the place where we end. But that terminal arm could be anywhere around the circle. The other way I remember that it's called a terminal arm is if you think of like a terminal illness, someone who has a terminal illness, that's where their life is ending. In the same way, this is where our angle is going to end. So it starts always at the initial arm and it ends always at the terminal arm. Okay. So the actual angle itself is measured from the initial arm to the terminal arm like this. And we often denote that angle with the Greek letter theta. It doesn't have to be theta, but we often choose theta. We like theta, sometimes alpha. And that represents that angle. So if I'm going like I did in that direction, I'm starting at the initial arm here and going up toward the terminal arm, this is a positive angle. If I go in the other direction, if I start at the initial arm and I go down this way, then that's a negative angle. So both can be housed in the Cartesian plane, which is pretty cool. Once we've drawn these two arms, the initial arm and the terminal arm of the angle, then we are able to make some other judgment calls about the trig ratios for such angles, okay? So if I drop a vertical line down to the x-axis, wherever my terminal arm is, I'm creating a right triangle. Now that right triangle is something that I can use my basic trigonometric functions with. So if this is like a point somewhere on that terminal arm, then I can create this triangle. I can figure out like the side lengths of that triangle, which would correspond to the points, like the values, the coordinates, x and y that get me to that point. So we know horizontally this is our x-axis, vertically this is our y-axis. So this side along the bottom here is our x side, okay? And this side along the side here is our y side. Truly, they're not really sides, like we're talking about how far left and how far up we're going in this particular case, or how far horizontally and how far vertically we're going, because it could be right or left and up and down. And so this would end in that point, xy, at the top there. Now, the third side of this triangle that we've drawn is often called R, and it's called R because of a radius, okay? We're trying to kind of always imagine that as you spin your terminal arm around the circle like this, that the radius is always the same. And so as I'm drawing this around the circle, my angle is changing at every individual point where I'm lying on the circle, but what's not changing is the radius of that circle. So the radius is always considered to be a positive value, but of course x and y have different signs in different parts of the Cartesian plane. So now, because we've drawn this right angle triangle, we are able to use our primary trig ratios, sine, cos, and tan, as well as our secondary trig ratios, which we'll review really quickly in just a second, to be able to identify the value of the ratio for specific angles. Or in other cases, if given the ratio, we can use the ratio to find out what angle it is that we're talking about in the Cartesian plane. So in grade 10, when you first learned about trig, you learned about opposite, adjacent, and hypotenuse. We were just talking about any kind of right triangle living in space out here, not pinned to the Cartesian plane, where if your reference angle is here, then the side that was longest in that triangle would be called the hypotenuse, and the side that was adjacent to that angle but not the hypotenuse was called the adjacent side, the one that's next to, it's attached to that angle. And then the last one is the opposite side. It's the one that's furthest away from your reference angle. So in grade 10, this is how we looked at it. And now in in grade 12, we're looking at our angle, which is theta. That's the principal angle that goes all the way from our initial arm to our terminal arm like this. But we have to kind of look at the related acute angle that's inside the triangle as well. So that's this guy right here. And we often call this one beta, that related acute angle. We'll talk about those again in a second. So, like I said before, the angle that we're focused on is always sitting at the origin. It's never, ever, ever going to be up top there. So don't ever look at that angle as we're working with triangles in the Cartesian plane. So, okay, so now let's talk about the signs a little bit. So in this particular example, we can see that the terminal arm is in the second quadrant, okay, up on the top left quadrant. And so when we evaluate our sine, cos, and tan ratios, the sign of those values matter because while we're in the Cartesian plane, this value of x is negative over here. It's on the negative side of our x-axis. This y value is a positive value up here. We're on the positive side of that vertical axis. So any values that incorporate x or y are going to be impacted by the signs. The radius, however, is always positive, as I mentioned earlier, because it's just considered a distance to the origin, and a distance is never really considered to be negative, whereas x and y, they tell us position, so they have a sign. All right, so in grade 9, in grade 10, when we looked at sine, cos, and tan, we just use opposite, hypotenuse, and adjacent. And then in grade 11, we introduced that language of x, y, and r. But kind of, putting those two together, because our angle is here at the origin here, like really our principal angle is this one, but we're kind of using our reference angle for the time being while we're over in this quadrant. Then the y is our opposite side, the x is our adjacent side, and then the radius is our hypotenuse. So using all that, we know that sine being opposite over hypotenuse is the same thing as y over r, cos is x over r, and tan is y over x. Okay, so that's all familiar to you from grade 11. So now using those ratios, we can talk about the sign of each of the our trig functions, sine, cos, and tan, in each quadrant. So for this quadrant here, when I'm talking about sine of theta, I'm talking about that angle that goes from the initial arm to the terminal arm, from here to here. Then here we have y over r, and that's a positive value over a positive value. Okay, so sine is positive here. Okay, when we're looking at cos, however, cos has that x in it. So we have this negative value of x over a positive value of y. Okay, so that means that we're going to end up with a negative over a positive, so overall a negative value. And same thing with tan. Because tan also incorporates the x value, which is negative, then we have y over x, which is a positive over a negative, and we're left with an overall negative value. So if you remember from grade 11 that in this quadrant over here, sine is our only positive trig ratio in that quadrant. If I move over into the first quadrant, then our angle may look something like this. So we can see if we create that right triangle by dropping down a vertical line from some point that's on our terminal arm, that this point xy now gives us a positive value of y and a positive value of x, and then of course the radius is always positive. So of course, whenever you evaluate any of these, y over r, x over r, or y over x, they're all going to be positive in this quadrant. When I'm over in quadrant 3, then we know in this area, this is the negative side for x. It's also the negative side for y on our Cartesian plane. And again, r is always positive. That's a positive value there. So now this time, when we're looking at the sign of each of those trig ratios, we know that any of them that involve a y or an x only with the radius, those will be overall negative because they have one positive value of radius and one positive value of either x or y. So those are sine and cos. So sine is going to be negative here because it's negative y over a positive r, so overall negative. Cos is also going to be negative here because it has a negative value for x over positive value for radius, which is overall negative. But tan, because it has two negatives, it has the negative y and the negative x, we get an overall positive value, right? Because negative y divided by negative x will give me a positive value. So in that quadrant, we have tan is the only positive value, so it's kind of special. Now for an angle that's in the fourth quadrant, we know that we are on the positive x-axis side over here. We are on the negative y-axis side down here, and the radius is always positive. So here we know that sine is going to be negative because sine involves the y and the r. So a negative over a positive is going to be an overall negative value. So sine is negative down here. And we know that cos is going to be positive though, because cos has a positive x and a positive r, so we're left with a positive value for cos. And then we know that tan is negative because tan is that negative y over the positive x, which is overall a negative value for tan. So in this quadrant, the special ratio is cos because it's positive. Often people refer to this as cast rule to help us remember who's positive where, but I really like the way that Mr. Porto thinks about it, which is remembering just by the ratio. So for sine, we can see that sine is, everybody's positive here, right? Sine is positive there and at the top. So sine is like positive all across the top, okay? Whereas cosine is positive in that first quadrant where they're all positive, of course, and down here. So cosine is positive on the right-hand side of our Cartesian plane. So that leaves that tan is positive in that first quadrant where everybody's positive, and in this quadrant over here. So these are the ones that are diagonal across from each other. This is where tan is positive. Okay, that's quite messy. You can't really read that, can you? Okay, let's just go with tan. Cool. So this is also referred to as cast rule because it helps us remember, if you can remember what goes where, that they're all positive here, so we put an A in that spot. And cos is the only one positive down here. Sine is the only one positive over here, and tan is the only one positive over here. So we call this the cast rule. Some people get confused though because of course it doesn't start in quadrant 1. It starts down here in quadrant 4. This is quadrant 4, this is quadrant 1, this is quadrant 2, and this is quadrant 3. So some people find that tricky to remember where the C starts in cast. But whatever it is that you use to help you remember what's positive where, or you don't have to memorize any of it, and you can just look at the value of x and y in that quadrant. So you know the radius is always positive. So overall, when you look at these ratios, y over r, x over r, y over x, do you get a positive value there for that angle? So the last thing for this slide is to address what we hopefully remember from grade 11, which are the reciprocal trig ratios. And we know that reciprocal just means like take a fraction, flip it upside down, the numerator becomes denominator, the denominator becomes numerator. So the same thing is true for these functions when we're just looking at their ratios. So cosecant is the ratio of the radius to the y value. Secant is the radius to the x value, and cotangent is x to the y. So they're the same, like have all the same ingredients as their primary counterparts, but just with their fractions flipped upside down. We'll spend more time talking about what those functions actually look like later on in the unit. But for now, all that's important for us to say is that the signs will be the same, okay? Because cosecant and sine have the same ingredients of y and r, they're going to be positive and negative in the same quadrants. And because secant and cosecant have the same ingredients of x and r, they're going to have the same sign in each quadrant as each other. And because tan and cotangent both have x and y, wherever tan is positive, cotangent will be positive. Wherever tan is negative, cotangent will be negative, etc. The last little bit of terminology that I want to go over from grade 11 is about coterminal angles and related angles and principal angles as well. So in all of these, theta is like the big one that goes from the initial arm to the terminal arm. So we have one in each quadrant, so you can see what those all look like this, right? That's kind of the main thing. That describes where that terminal arm is with the principal angle. That's what's in purple there. Now, for each principal angle, there is a related acute angle. So the related acute angle is just like the smallest angle that gets that terminal arm to the x-axis, okay? So that angle, when we're talking in the first quadrant, is the same as the principal angle because the terminal arm is acute, or in that first quadrant, making that angle acute. So that's the related acute angle and the principal angle are the same. But when we're in a different quadrant, so we're over here in quadrant 2, then we can see the principal angle is obtuse, right? But the related acute angle is always acute. It's just the smallest angle that joins the terminal arm to the x-axis. It's always, always, always the x-axis. It's never, never, never the one that goes here between the terminal arm and the y-axis. We don't use that angle for anything when we're talking about in the Cartesian plane, really, so don't get in the habit of using that guy. When we're in the third quadrant, our related acute angle is just this small one that just goes from the terminal arm to the x-axis in the nearest way possible. And then in the fourth quadrant, it's down here. Okay, so, oh, and I just realized actually that this diagram is really misleading because this isn't the principal angle really at all. This angle theta should be this guy. This one is the principal angle over here. This one is a coterminal angle. It's coterminal with the principal. Coterminal. See if I can spell. That happens to be negative. Okay, this one's negative because it goes from the initial arm down to the terminal arm in that downward direction, so it's a negative angle. But anyway, the key thing that I was trying to get at there was the related acute angle. So the related acute angle is always that little guy that joins the terminal arm to the x-axis in the nearest way possible. Never, 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 never with the vertical axis, okay? Always with x. Okay, so let's kind of jump to that idea of coterminal. So coterminal angles are just angles that share a terminal arm. So that means that they start and end in the same place. They all start at the initial arm and then they end at the terminal arm. But they might go in different directions. They might go around the circle multiple times. But that's what makes them coterminal, is that they share that starting and end place. So for example, in this first quadrant, we'd have a coterminal angle that goes all the way from the initial arm in the same direction and then ends up at that terminal arm as well. That would be coterminal with that original angle theta. Maybe it's called alpha, just some other angle that goes to the same place. Or we could have an angle that goes in the negative direction from the initial arm to the terminal arm. So still starting along the initial arm, the positive x-axis, and still ending at the terminal arm, but just maybe going in a different direction, or maybe taking a long way around, like going around the circle a couple of times first. So coterminal angles, we can make an infinite number of them as long as we start and end in the same place. Doesn't matter what direction we go in. I mean, it matters in the sense that it changes the measure of the angle, but not in the sense of whether or not they are coterminal. So they can be positive and negative, going as long as they start and end in the same place. They are considered coterminal.